Have you ever wondered what our universe is really made of? Like, what's at the very bottom of everything? What makes you, me, the stars, and even your phone tick at the most fundamental level? Now imagine this: everything you've ever known might just be vibrations of tiny invisible strings. That might sound like a line from science fiction, but it's actually a serious theory in modern physics. Today we're diving deep into a realm so bizarre, so counterintuitive, that even Einstein had trouble accepting it. Welcome to the wild world of quantum mechanics and string theory, where reality begins to break apart and reassemble itself into something you've never imagined. All the matter we see around us, every tree, every drop of water, every speck of dust floating through space, is made of tiny building blocks. But what are these blocks made of? Are there smaller things inside them? And how far down can we go? These are not just philosophical questions. They are central to one of the most intense areas of scientific research ever undertaken. We're talking about theories that try to describe how nature behaves at its most fundamental level, on scales smaller than atoms. It's not just about matter. It's about the forces, the interactions, and even the rules of reality itself. Now let's talk about one of the people who's been at the forefront of this quest, American theoretical physicist Michio Kaku. He's famous for making some of the most complex ideas in science seem almost understandable, even to people who've never opened a physics textbook. Kaku works on quantum mechanics and more specifically, on something called string theory. He doesn't just explain it, he lives it. In his own words, string theory is his day job. And it's not just any theory. It's a theory that suggests our universe might be one of many, a multiverse. So what is string theory exactly? According to Kaku, it's actually pretty simple at its core. It says that all the particles we've discovered, the electron, the proton, the quarks, are not little dots but tiny vibrating strings. These strings are unimaginably small, much smaller than atoms. And just like how different vibrations on a guitar string produce different musical notes, different vibrations on these fundamental strings create the different particles we see in nature. Everything from the tiniest neutrino to the massive top quark could just be music, played on the tiniest strings imaginable. To really understand why this matters, we have to go back in time. In the 1950s, physicists were discovering new particles left and right using massive machines called atom smashers. It got to the point where Robert Oppenheimer, the man behind the atomic bomb, joked that the Nobel Prize should go to the physicist who didn't discover a new particle that year. The field was overwhelmed by a zoo of particles and it seemed like chaos. But what if all those particles weren't random at all? What if they were just different notes played on the same kind of string? That's the magic of string theory. It brings order to the chaos. It suggests that physics is like harmony, the different vibrations you can create on these strings. Chemistry? That's the melodies you play. And the universe? It's a full symphony of strings, all vibrating together to create the rich diversity of everything we see, touch, and experience. Suddenly, reality isn't just particles flying around. It's music at a scale far too small for us to hear. But before we get too deep into strings, let's pause and talk about quantum physics itself. Because trust me, it's already weird enough. Quantum mechanics is the framework that describes how things behave at the atomic and subatomic levels. But it doesn't work like the physics you and I are used to. In our everyday world, if you throw a ball, it moves in a predictable way. In the quantum world, a particle can be in multiple places at once. It can act like a wave and a particle at the same time. And get this, just observing a particle can change how it behaves. That's not just strange. That's straight up spooky. In fact, Albert Einstein himself called this spooky action at a distance. He was referring to something called quantum entanglement, a phenomenon where two particles become linked in such a way that changing one immediately affects the other, no matter how far apart they are. It's as if the universe has a secret line of communication, faster than light. Einstein didn't like that. He believed there must be a hidden reality underneath, something we couldn't see but that made everything make sense. But as more and more experiments were conducted, Einstein's skepticism was slowly overshadowed by solid evidence. And this leads us right back to string theory. Because while quantum mechanics is already strange, string theory takes it to a whole new level. According to string theory, particles aren't little dots. They're tiny loops of string, each one vibrating in its own way. And those vibrations? They're what give particles their mass, their charge, and all their other properties. It's like tuning a stringed instrument. Each note is a different particle. And if you tune the strings just right, you get electrons, protons, quarks, and maybe even particles we haven't discovered yet. What's even more incredible is that this idea isn't as new as it seems. Thousands of years ago, ancient Greek philosophers were already asking similar questions. One of them, Democritus, believed everything was made of tiny indivisible units called atoms. Meanwhile, his rival Pythagoras thought the universe was built on music. He noticed that longer strings produce lower notes and that there's a mathematical relationship between length and pitch. He believed that this same harmony governed the entire universe. At the time they couldn't prove any of this. But the idea stuck around for over 2,000 years. Now, modern string theory has finally brought those two ancient ideas together, atoms and music. Today we can say that atoms themselves are made up of particles, and those particles might just be different notes on vibrating strings. So when we ask why there are so many types of particles, the answer could be simple. Each one is just a different vibration. The electron vibrates one way. The quark vibrates another. The neutrino has its own unique tune. Suddenly the particle zoo doesn't seem so messy. It's just a complex song played by the universe. But string theory doesn't stop there. It also opens the door to one of the most mind-blowing concepts in physics, the multiverse. If the math behind string theory is correct, our universe might be just one of many. There could be other universes out there, each with its own laws of physics, its own particles, even its own versions of you. We don't have solid proof for this yet. It's still theoretical. But the implications are enormous. It means that reality as we know it might just be one note in an infinite cosmic symphony. And still, despite all our progress, the quantum world remains one of the biggest mysteries in science. Some of the greatest minds have tried to crack it and even they struggled. Albert Einstein, for example, spent the last years of his life trying to find a unified theory, a single framework that could explain everything from gravity to electromagnetism to quantum mechanics. He never finished it. In fact, when he died, newspapers around the world published a photo of his desk, and next to a caption that read, "This is the unfinished manuscript of the greatest scientist of our time." For a young Michio Kaku, that photo changed everything. He was just 8 years old when he saw it, and it lit a fire in him. He thought, why couldn't Einstein finish it? What was so hard? That question stayed with him. And now, decades later, he's still chasing the answer, still trying to complete what Einstein began. His work in string theory isn't just about particles. It's about finding the ultimate truth, a theory of everything. A single, elegant equation that explains the entire universe. And as we peel back the layers of reality, from atoms to quarks to strings, we get closer and closer to that answer. But the journey isn't over. In fact, it might just be beginning. So, think about this. A great scientist had what looked like a homework problem. Just one equation, right? So why couldn't he solve it? That question stuck with me. To me, this wasn't just some math issue or forgotten notebook. This was a full-blown mystery, the kind that grips your imagination. It felt like a murder mystery, something bigger than any adventure story I'd ever heard. I couldn't understand how one of the greatest minds of all time could leave something unfinished. That curiosity burned in me and I just had to know what had gone wrong. Why couldn't he complete it? As the years passed and I started learning more, I eventually found out who the man was, Albert Einstein. And that mysterious, unfinished book he had been working on? That was his attempt at the theory of everything. He never got to finish it. But today we can look at that book. We can flip through its pages, trace all the ideas he tried and abandoned, the false starts and the dead ends. And through that, I began to see where he lost his path. What became clear to me was that he didn't have a physical image, something visual, to guide him anymore. On his first try, Einstein used real-world analogies like clocks ticking, lightning bolts striking, and meter sticks stretching. These helped him imagine how time and space work together. That effort gave us special relativity, a theory so powerful it laid the groundwork for nuclear energy and, eventually, the atomic bomb. Then came the second major attempt. This time he visualized gravity using curved surfaces and rolling balls. That helped him create general relativity, which led to the Big Bang theory, the expansion of the universe, and our understanding of black holes. It was revolutionary again. But it was on his third and final attempt that he faltered. He didn't have that same kind of visual aid to guide his thinking. There was no intuitive picture he could lean on. And that, I believe, is where he lost his way. Fast forward to today and we think we may finally have that missing image Einstein needed. It's called string theory. This theory doesn't just update our understanding of physics, it reimagines the very building blocks of the universe as tiny vibrating strings instead of point-like particles. These strings might hold the answer to unifying all the forces of nature. String theory also proposes something that feels almost impossible to grasp: extra dimensions. Not just the three spatial ones we know, length, width, and height, but many more curled up in shapes too small for us to see. It's a mind-bending idea. But it's not just science fiction. According to this theory, these extra dimensions are real and necessary. And they open the door to an even wilder concept, that there might be multiple universes, each with its own unique laws of physics. This is the multiverse, an idea both thrilling and terrifying to consider, and now a serious topic of scientific debate. According to this view, every time a decision is made, whether it's a particle interaction or a flip of a coin, the universe could split, with each possible outcome happening in a different universe. In one universe you turned left, in another you turned right. It's hard to wrap your head around, but string theory suggests that such branching realities could exist, and they might all be as real as our own. What was once just a sci-fi concept has now become a valid area of theoretical physics, drawing intense curiosity and research from the scientific community worldwide. String theory could even help explain one of the biggest mysteries in modern science: dark matter. This invisible substance makes up about 27% of everything in the universe. We can't see it, we can't touch it, but we know it's there because of the gravitational effects it has on galaxies. One possibility is that dark matter is made up of something called WIMPs, weakly interacting massive particles. These hypothetical particles might be produced by the same tiny vibrations of the strings at the heart of string theory. If true, it would be one of the biggest discoveries in physics. Yet, despite its promise, string theory remains full of uncertainties. There's still so much we don't understand, and even more that we haven't proven. But one thing is clear: this theory has opened up entirely new avenues of thought. It's challenged us to rethink everything we know about reality. It's reminded us that the universe may be far more intricate, strange, and wondrous than we ever dared to imagine. And that alone is powerful. But at the same time, for a theory to truly stand the test of time, it has to be more than just imaginative. It has to be testable. And that's where string theory faces its biggest challenge. The scientific community has not been shy about pointing this out. One of the biggest criticisms is that string theory is very difficult, some say impossible, to test or falsify. It depends on extra dimensions that are far too small to observe directly. We can't build instruments precise enough to detect them, at least not yet. And this lack of experimental proof has made many physicists cautious. Science depends on being able to verify ideas through observation or experiment, and right now, string theory struggles in that regard. Another issue is that, despite decades of mathematical exploration and intense effort by thousands of brilliant minds, string theory has yet to produce a single testable prediction. No experiment so far has confirmed it. That's a real concern. A theory, no matter how beautiful or elegant, has to make predictions that can be measured and observed in the real world. Without that, it's still speculation. Many critics argue that string theory might be too complex and too dependent on unobserved particles, exotic scenarios, and other universes we may never be able to see or confirm. Still, even with all these criticisms, many physicists believe it's worth pursuing. The reason is simple: string theory aims to solve some of the deepest and most important mysteries in science. If it can unify gravity with quantum mechanics, the force that governs the large-scale universe with the rules that control the microscopic world, it could truly be the theory of everything. And that's worth fighting for. But we must also remain critical. We must keep questioning, keep testing, and keep exploring other ideas. The goal is to find the truth, not to fall in love with a particular theory. And that's true for any scientific field. When something is new, of course it draws excitement. News headlines buzz, students rush in, and the public gets fascinated. It's fresh, novel, and full of potential. But as that field matures, it naturally loses that shiny new thing appeal. It settles down. That doesn't mean it fails, it just means it needs to be judged differently. Instead of asking whether it's still exciting, we ask whether it's deepening our understanding. Is it helping us answer the big questions? Is it making progress even if it's slow? And by that measure, string theory is doing well. String theorists themselves are very aware of this. Most of them, including myself, are not overly romantic about it. We're sober in our view. The glory days of massive breakthroughs, like those of the 1980s and 1990s, may have faded, but that progress wasn't lost. In fact, we've become more prepared to handle what lies ahead. We now better understand how long the road is. Yes, the theory still faces major challenges. Yes, we're still waiting for experimental contact. But in terms of foundational insight, on the deepest structure of matter, space, and time, string theory continues to score remarkably high.